All right, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 318, Electronic Circuit 1. And today is our 21st lecture. And can you guys hear me well?
Yep.
All right, thank you, Josh. So we can move on. First of all, based upon some questions of the homework problem, I'm going to talk about one or a couple of them in the lecture at the beginning today. And the first question is about the homework 4, problem number 4.33, section C. Yeah, the section C is looking for the output resistance or not for the given circuit. Now the circuit is repeated on the paper like this, okay? And looking for the output resistance or not. Okay? Let's see how to do this. Okay, let's see how to do this. Okay. First of all, you need to understand that what this output resistance or not is referred to what AC, a small signal. Okay. Circuit. It's not talking about the DC. It's not talking about DC. So basically, DC is taking care of the biasing, trying to locate your Q point to somewhere you want, and that's it. Okay. DC is should not playing any other role. Okay. Of course, it's affecting the output. The output might have a DC offset because of the DC supplies, but still that's not that should not affecting the or not the output resistance. Okay, so the output resistance here, you need to first of all again be clear. It's talking about a small signal circuit. A small signal circuit of this given circuit is fairly easy, right? We plot like this, and we realize this is in channel, right? So this is GSD like this. This is small signal model, of course. According to the problem parameter lambda, we know we need to involve what? R naught. R naught is involved, okay? And this is the small signal model of the transistor itself. Now we're extending the terminal we're extending the circuit terminal by terminal. First, the gate. Now the gate, according to the given circuit here, the gate is connected to the input source. The other terminal is the ground, right? This is the gate. And then the drain is what? Ground, right? You realize this is ground. The source is connected to where? RS. And then the other terminal is shorted with the ground, right? This is the AC small signal circuit, first of all. Okay. Small signal circuit. And obviously, this is a common what? Anyone notice this is a common what? Well, of course, the original circuit, you have output voltage here. So this is a common what?
Drain.
And common drain. It's common drain. It's common drain. Right? This is a complete small signal circuit. From here, once again, what I did in the lecture example is what? Flip this part of the circuit down. Right? Flip it down so that I can short the drain ground with this ground down here. In other words, I'm going to do this. I'm going to do this. So down here, this is a drain, as I said. Up here is the S. Remember, if we flip this circuit down, and here is GM, VGS, VGS obviously is here. Right. It's VGS. And then we move on. How to find the output resistance? What's the idea? The basic idea. What do you have? Anyone knows? Yes, we didn't do much about it before, but we did mention how to find equivalent resistance across two ports of the circuit. We did mention this before.
Wouldn't you use Thevenin's theorem?
It's close, but I don't suggest you to kind of mixing the concept of Thevenin and the equivalent resistance. One thing, yes, in finding the Thevenin equivalent circuit, you have to find its Thevenin equivalent resistance. However, that Thevenin equivalent resistance is not the equivalent resistance across any two ports. I suggest you to differentiate these things. Okay, differentiate this. They're not exactly same. They're not exactly same. Very close. So how to find the equivalent resistance? Because output resistance now means what? Between which two ports in this circuit? Is that clear? Output resistance now is between which two ports? You need to understand this first of all. Right? Which two ports? Anyone knows? Anyone? Well, obviously you need to know where this R0 is, right? Otherwise, what are you doing? There's no target then. You're shooting towards nowhere then, right? Where is the R0? Is that clear? Anyone? Really? Not clear? Well, output resistance is at output, right? However, it's across two ports. Which two ports? Output and what? Ground. And ground. Therefore, this is the output resistance we are looking. Okay, it's labeled in this way. So how to find this output resistance? We are adding the test source. We call it Vt. And then therefore introducing input current, which is IT, right? And what else do we need to do? When we do this, we need to what? Because in the circuit, we are seeing one independent source and one dependent source. To dependent source, what's the principle? No matter what, you can't touch, remember? We always follow this. No matter what, you can't touch the dependent source. It is there forever. Superposition, the Thevenin, or now you're looking for the equivalent resistance. No matter what you are doing, you can't touch the dependent source. It is what it is. Okay. However, what about this guy? This is the independent source, right? Independent source, what we should do? Short it. Okay, here we go. In other words, get rid of it. Get rid of it. Okay. Shut it off, or say. Okay. Since this is a voltage source, so shut it off by shorting it. Now, this is the result of circuit for you to find R0. And being very clear, R0 is a ratio between two unknowns, Vt over It. And also being very clear that in terms of math, algebra, we're not going to be able to find Vt and It individually. we can only find the ratio between them, which is R0. Okay, so if you're expecting to find VT value, IT value, that's impossible. Okay, that's impossible. You can only find the ratio between them. Okay. All right, now, if all of these concepts are clear, then the next is just time to write equations, right? What equation we can have? What equation we can have? Well, first of all, how about let's have a KCL at source up here. I'll be including here as well. This is what? What is it called in circuit 1? Anyone still remember?
It's a super node, isn't it?
A supernode, it is. A supernode on top, which is the source. It's KCL at source. What do we have? First of all, how about VT over RS parallel with R0? Well, this is what? Current flow downwards through RS and R0 in total. Does it make sense? Because RS and R0, they're parallel. They're nothing but parallel, right? The downwards, okay. The numerator is VT minus 0, or say. Okay. This is minus 0 divided by the resistance. Receive a current downwards. Equals to what? Anyone? Anyone knows equals to what?
Would that be negative GM VGS?
Equals to.
What he said without the negative.
Exactly. Very good. And don't forget IT. Come on. 1, 2, 3, 4. 4 branches, 4 current. You can't just end up with 3 current. And this now, if you cover IT, then you only have 3 current. Does it make sense? All right. This is the KCL at the source. And of course, we can count how many nodes? BT, VGS, IT, 3 nodes, 1 equation. No, we can do nothing. We need one more equation. Can anyone tell what is the next equation? Can anyone tell from the circuit? Probably a little bit tricky to find, but it is there. Can anyone tell?
VGS equals negative VT.
Very good. VGS equals to negative VT. And how we get there? Josh?
Let me just check the polarities of the source and the test source, or VGS and the test source.
Okay.
That's determined by the current direction, IT.
And
That would mean that IT is going through the negative terminal of VT, which makes it negative VT, and then IT is going through the positive terminal of VGS, therefore making it VGS equals negative VT.
not exactly.
No.
Well, the thing is this, right? The VG here is equals to what? VG equals to what? 0.
Yeah.
VS equals to what?
VT.
Vs equals Vt, good. Therefore, VGS equals to what? Vg minus Vs. Does it make sense? This is the definition of the voltage potential. And then you substitute 0 and Vt in, and then you got this equation.
Okay, that makes sense.
All right. This is how you got this equation, or say, this is how you're supposed to get your equation. And now you have three equations, two equations and three unknowns. Done. Done. Of course, I have ever been asked how to conduct this algebra. So let's go through this algebra. How to do this algebra? Keep in mind, which one we want to substitute so that it will be gone. Which one? Anyone knows? The three unknowns, right? Which one we need to get rid of by substitution? And why? This is the key for you to conduct this algebra for next step. Right? So whom you want to get rid of? Obviously VGS, right? Obviously VGS. You want to substitute VGS by something else, by VT and IT. So in the rest of the equation, you only have VT and IT. Therefore, you're able to find a ratio between them. Does it make sense? So in the first equation, you have a VGS over here. And second equation, very convenient. The VT over RS parallel with R0. This is the first equation. Substitute VGS in the first equation by second equation. Right? Whether it equals to right? From here, immediately you got a ratio. 1 over S parallel with R0 plus GM. Done. This is the solution. And of course, can anyone realize this is also equals, this solution also equals to what? RS parallel with R0 parallel with 1 over GM. I don't know if you can see this. If you can't, but this result remains same, remain correct. So that's okay. But you can, if you can see this, then it equals to that. So any questions? Any questions? Is it clear now?
Yes, thank you.
Sure, no problem. All right. And I have received another question from another student asking homework 4 problem 4.24a. Well, this question is a little bit tricky, because you can only find 3 equations, but you have 4 unknowns. But the solution is this: you're choosing RS value. Okay. You're choosing RS value. Therefore, RS is not unknown anymore. It's chosen as a value. Accordingly, you find the rest of the voltage or other values. This is how to deal with this. Okay, you're choosing RS value. The textbook solution providing a choice as 10 kilo ohm. We can follow. This is how you deal with the RS. one of the unknowns. Because from the equation, from the circuit analysis, no, we can't find out the RS value. We have to choose a value. Okay. All right. Any other questions regarding the homework, regarding the course, even? Anything? And here, if nothing, we can move on here. So I'm bringing up this pattern, or we'll say this summary table once again. Okay. So we basically have done I don't know why, but every time I can't use the depends on the on this PT slides. But anyways, so obviously we have done everything about diode. We have done everything about MOSFET. Now we are here. Start to learn the basics, DC and AC analysis for the Bdt. Okay, so this is the pattern. The Bdt is very close to MOSFET in many ways. Okay. However, you want to be careful the difference as well. Okay, so we will see that. And the most important thing for this course, for this entire course, is obviously the DC and AC concept and the circuit analysis for MOSFET and Bdt. Because in following 358 electronic circuit 2, you're gonna use these basic knowledge to analyze more practical, more complicated circuit. Okay, different other circuits with different functions. All right, this is the chapter 5, the Bdt. The full name, first of all, is Bipolar Junction Transistor. The Bipolar Junction Transistor. And it has 3 terminals, okay, same as the MOSFET. And here, the applications-wise, we are trying to combine the Bdt and MOSFET, or say put them together to do a comparison. Okay. So first, in terms of applications, both can work as a switch. Okay. So first here, both can work as a switch. Okay. So-called switching applications. And voltage or current at one terminal controls the open or closed, or say off and on condition between other 2 terminals. So we can see the on and off switching behavior from the IV curve as well. Okay, different operation region, basically. Right? And the both can also work as amplifier. Okay, continuous control amplification. So the voltage or current at one terminal controls the current flow between other 2 terminals over a continuous range of values. So this is very popularly used in analog circuits. Okay. So even including the diode can only be used as a switch, on and off, 2 states, very simple. So either forward biased as on, or reverse biased as off, right? The diode is super easy. The transistor, MOSFET, could be either switch or amplifier. And to work as amplifier, you need to make sure your DC circuit is biasing your Q point in the saturation region. To work as switch, you need to make sure your DC is biasing the Q point in the non-saturation region. Non-saturation region. Well, of course, if you bias your Q point into cutoff region, that's off. The transistor is off, right? To Bdt similarly. If you want your Bdt works as a amplifier, what you need to do is using DC circuit to bias your Q point into one region, which is not called saturation region, but called active region. This is obviously a very clear difference. Right? Cannot use the, okay. Active region. And to make Bdt works as switch, you need to bias your Q point into what region. Be very careful, the name is a little bit tricky. It's not called non-saturation region, but called saturation region. For Bdt, the saturation region is representing the on state of the switch. Be very, very careful of this name. And off state remains as cutoff. Okay, it's called the cutoff. Okay. This is a little bit summary here. Of course, once again, be very careful which region it is working at, or depending on the DC, or depending on your DC circuit, how to bias your Q point. Okay. Further, keep comparing with the MOSFET. Okay, the Bdt has what? Same as MOSFET. Okay, the inputs apply to the control terminal. This time, control terminal is not gate, but called base. Okay, so it's not GDS, but BCE. Okay, and the base is the control terminal. And the current flows through this control terminal to control the other two terminals, voltage and current, okay, emitter and collector. And it's not same as the MOSFET. The Bdt's current flows into the control terminal base. Because in MOSFET, there is no current in the gate. And the gate current is 0, the open circuit. And also not same as MOSFET, the Bdt's current is induced by movement of both electrons and holes. Therefore, it is called bipolar. Remember the full name of the Bdt? Bipolar junction transistor, right? The bipolar. Two types of Bdt, two types of MOSFETs are N-channel and P-channel, and two types of Bdt are called Npn and PNP. What does it mean by Npn and PNP? It's very easy. It's, basically, you can understand in this way, okay? Npn means you have two N-type of semiconductor, and in between, you have a P-type of semiconductor. You have two types of semiconductor, one type and a P-type. You squeeze a P-type semiconductor in the middle between two N-types of semiconductor. Here we go. It's a Bdt, Npn, right? Npn. And two N-type semiconductors are respectively emitter and collector. And in the middle, the base is P-type semiconductor. And this, excuse me, this is the rough structure. Okay, the real structure is not as easy as this. Okay, this is just to give you a kind of understanding. Okay, 3 terminals: emitter, base, and collector. And from here, you can also understand a Bdt as what? Back-to-back PN junctions, right? Back-to-back PN junctions. What does it mean by back-to-back PN junction? It's basically meaning what? 2 series connected diode. Make some sense? Okay, because 1 PN junction is 1 diode. Right? Diode is also called PN junction diode. Right? So 1 PN junction here between P and N. Another PN junction is here between P and N as well, right? The 2 diodes back to back, right? And of course, don't take it wrong, okay? The actual Bjt structure is much more complicated than this, and it is not symmetrical. It is not symmetrical. Okay? This is just showing you the idea. The real one is much closer to this one. Okay, this is structure in detail. You have substrate here, and then you are doping different types of semiconductor on the top of it, right? And forming the PN junctions. Okay. Now let's talk about the behavior of the Npn Bdt. Okay. So to Npn Bdt, the emitter is a source of large electron current that flows across the forward biased BE junction. B is base here. E is emitter here. Okay. There's a junction in between. Okay. The voltage drop potential between base and emitter. If you see that. And the most important thing is obviously down here. So the emitter is way bigger than the base current. Okay. And the emitter current is way bigger than the base current. And it is also equals to what? The summation of collector current and base current. Okay. Since emitter current is way bigger than the base current, therefore the emitter current is approximately equal to the collector current. Does this make some sense? Okay. Emitter current is close to collector current. Okay, very close. And the difference between them is nothing but the base current. Very, very tiny. Remember today's lab? IB is in what? Microcurrent, microampere, right? IC is what? Milli, right? That's really, really different. That's a big difference. That's a big difference. And to Npn Bdt, what's the current direction? You need to understand. Collector current is flowing into the Bdt. Base current is flowing into the Bdt, and the emitter current is leaving the Bdt. Okay, you need to understand the current flow direction. Of course, in circuit simple, the arrow can tell you that, but here we bring up at the first place. Okay. The current direction absolutely makes sense. However, don't consider the Bdt as a node, okay? Because from here, your IB going in, IC going in, the sum of these two going in equals to the current, total current leaving it, which is IE. It sounds like this transistor is what? Nothing more than node, right? You don't want to think in this way, okay? This relationship is correct. However, don't consider the transistor as a node, okay? Because it's pretty much a KCL, right? However, it is not that simple. It's not that simple. Okay. And a little bit more model for IE and IC, and they're actually internally depending upon the VBE and the VT. But these are not the formula we need for our DC analysis. So don't worry them too much. Okay. And here are the DC relationship among those current. Okay. Once again, repeating. Okay. Emitter current equals to the summation of collector current and base current. And here, this is something new. This is something new. What do you see? This is a current gain. Now, this is a current gain. Collector current is a gain beta times base current. This is a current gain. Okay, very important. It's a very important current gain. And because of this gain, if you substitute IC by beta times IB, and then you're going to end up with the gain between IE and IB. You can see it basically a gain plus 1. So if beta is really, really big, if this current gain is really, really big, basically IE equals to IC, right? Therefore, IB is negligible. Does it make sense? Any questions so far? All right, if this is fine, then we can move on. Similarly, if we talk about the PNP, okay, the second type. PNP, in terms of structure, of course, you can imagine as what? 2p-type semiconductor. And then in between, you squeeze in the n-type semiconductor, right? PNP. 2 p-type semiconductors are respectively emitter and collector. In the middle, you have a base. And also, a quite significant thing is what? The current direction is flipped. Right? So the emitter current is flowing into the transistor. And collector current is leaving the transistor. How about the base current? Leaving the transistor as well. So once again, the relationship among those current remains same, right? Emitter current remains equals to the sum of IC and IB. IE still way bigger than IB. And still approximately equal to IC. Okay. This is the PNP Bdt. And also, they're essentially IE and IC are related to the voltage between emitter and base, but not VBE anymore, but the VEB. Okay. It's just like in the MOSFET, N channel and P channel, we swapping the what? Subscripts, remember? It's not VGS, but VSG. Here, it's not VBE anymore, but VEB. To NPN, we have VCE. To PNP, we have VEC. Right? So, based on what we know from the MOSFET, BJT things actually becoming easier. They become much easier. However, be careful or say pay enough attention on the difference. Okay, on the difference. Like I said, current relations what remain same. Just the what opposite current direction. Okay? Opposite current direction. Yep, exactly same. Sure. And here, circuit symbol. So this, now we start to talk about a circuit symbol. And also identification of which type. Remember, 2 identifications. Of course, we're going to have 3, just exactly same as the MOSFET. Identifying terminals, identifying type, identifying the common circuit, right? But now it's just the basics and the DC, therefore there's no identification of the common circuit yet, okay? So by reading this page, actually, how we identify the terminal, it's not difficult, right? And now it's not difficult anymore. How to identify a terminal. So first of all, base is very easy, right? Right in the middle, very easy to be identified at the first place. And then how to differentiate collector and emitter. Similar, right? Similar to MOSFET. The terminal with arrow on it, regardless the arrow direction. Okay. That terminal is the emitter. Okay. And then the other one without arrow on it is the collector. Okay. Is the collector. Same thing here. With arrow, emitter. Without arrow, collector. Base in the middle. Okay. This is how we identify the terminal. Next, the type, NPN or PNP. NPN means what? NPN means your arrow direction is from base towards emitter. This is NPN. PNP means your arrow direction is from the emitter towards base, the other way around. So this is the PNP. Okay. I think it's much easier to accept and understand. Once again, based on the knowledge from MOSFET, right? So the arrow placement is determining the emitter. And arrow direction is determining which type. Okay. Any questions? Anything? All right, if this is fine, then we can move on. Once again, I like the summary. I like the summary thing a lot. Okay, we are parallel comparing MOSFET and Bdt. 3 terminals, GDS versus BCE. How do we identify them? Okay. Listed here. The source of MOSFET is the terminal with the arrow. Okay. The emitter of the Bdt is the terminal with arrow. And then how to identify the type, N channel, P channel for MOSFET, and NPN for Bdt or PNP. It's all depending on the arrow direction. Okay. The third one, identify 3 common circuits. This is now very easy, right? This is very easy. This is uniform, right? Between 2 transistors. It doesn't matter which type of transistor, right? We are identifying the input terminal. It might be G, might be D, might be S. It might be B, might be C, might be E, right? It doesn't matter which transistor, right? And then identify the output terminal. It might be 1 out of the 6 again, right? Oh, of course, 1 out of 5, because the one of them has been occupied by what? Input, right? So output is definitely 1 out of the rest of 5. And then the left terminal in the circuit is the common terminal. This is how we identify the common circuit. Okay. Any questions? All right, then we can move on here. This is the IV curve, or the IV curve. We have tried to establish them in today's lab, so very good. Okay, very good. And first of all, IV curve means IC versus VCE. Basically, this is the output current versus the output voltage. The voltage through this transistor and the voltage across it. This is the IV curve. Right? So based on different IB value, it's not like in the VGS, it's different VGS volt. It's not like the MOSFET, in the MOSFET, where different VGS introduce different curve, right? Here is IB. Different IB introducing different curve. And inside of this IB curve, of course, the look is basically, let's say, very close to that of the MOSFET. Okay, no problem. However, we have different region names. We do have very close regions location as well. However, we have different region names comparing to MOSFET's IB curve. Okay. Instead of saturation, non-saturation, and cutoff in MOSFET, we have what? Saturation, active, and cutoff. Okay. And also be very careful. This region in MOSFET is called what? Anyone remember? This region? No. Contained by the green circle, oval. What is called in the MOSFET? Non-saturation. Very good. And in the Bdt, what is called? Saturation. Okay, saturation. This is a little bit tricky, but remember this correctly. We have second green oval down here. In MOSFET, we call it cutoff as well. Okay, so this is the same name. The same name. Cutoff means the transistor is off, no matter it's MOSFET or Bjt. Right? Leaving the middle big area as our amplification, right? As our amplifier application. We call it what? In MOSFET, we call it saturation region, remember? But in Bjt, we call it forward active, or say just the active region. Okay. The middle part. This is the knowledge of the IV curve. And once again, it's VCE or VEC is upon NPN or PNP type. Yep, here is emphasizing IB is determining different IB curve. Okay. VGS is determining different IB curve for MOSFET. Okay. Okay. This is something same with MOSFET again, right? It's early voltage to early voltage. How do we find early voltage in MOSFET? We did the same, right? Reversely extending the IB curve, and all of them can converge into one point along the x-axis. That voltage value is nothing but early voltage, or say the negative of the early voltage. And the output resistance of the Bdt, wow, isn't it the same too? For MOSFET, what we have, R0 equals to VA over ID, right? IDQ. Now in Bdt, it's not ID, obviously IC, right? So VA over ICQ. Okay. The output resistance formula. And once again, is VA a big value or a small value? We had the same question back in MOSFET too, actually. VA is big or small? Anyone out there? Big. Now, why is big? Why it is big?
Don't we, I remember in the MOSFETs, we ignored it most of the time because the VA was generally bigger. So we ignored the R not, but I don't remember why.
Well, actually, what Kevin just said is the result of a big VA rather than the reason for it, right? So because VA is generally speaking big, therefore we ignore it. What does it mean by ignore it? Ignore it because your R naught equals to VA over ID in MOSFET. So if VA is too big, your R naught is too big. Too big resistance means what? Open circuit, right? Open circuit. That's why we ignore it. Okay. Why VA is big? By this IV curve, you can tell. Okay. The slope of the IV curve is actually very small, right? It's very, very small, the slope. Means what? The curve is flat, or say very close to flat, not exactly flat. If it is really flat, of course, they can never converge to merge to one point, right? So it's very close to flat, small slope. Therefore, it takes very, very long to reach the x-axis. Right? That's why VA, negative VA is far away from the origin point. That's why. This is the IV curve. This is very flat. This is not a steep curve. Once again, this part is same as MOSFET. And here, this is also similar phenomenon. Say if you're applying a forward biased voltage VCE too high, what's gonna happen? The curve, IV curve, go boost up, right? They boost up. What happened? This is what? What we call this? What happened? If you see a curve, IV curve like this means what? This portion. You can just jump off of the Bdt or any specific device. Just thinking of any electric device, IV curve, anything. If you're seeing the IV curve looks like this portion, what does it mean?
It's short.
Very good. Basically shorted, right? Basically shorted. We call it breakdown, that's okay. But basically what you're seeing is the current is boosted up without taking much increased voltage. This is how we interpret this phenomenon, right? The current goes up quickly without much different of the voltage, right? This is pretty much the shorted, or say close to short, which means your device is not being able to hold the voltage. The voltage is too big. It's shorted. Okay. Obviously, this is bad. That's absolutely bad. Your device should be able to hold certain voltage across it without being broken. Right? However, here, once you see such behavior of the current, that means your device is not able to hold anymore. Okay. It's broken. Okay. All right. Any questions before we talk about the DC analysis? Because even in the DC analysis, most of the things are what? The same as MOSFET. Similar pattern. Any questions regarding the Bjt basics? Because we have done the basics. Yeah, they're very straightforward. It wouldn't be if you don't have the background out of the MOSFET. Okay? But now you do, so it's really easy to you. Okay? All right, let's talk about the DC analysis, and then maybe with a couple of examples, and then we can call it a day. Okay? So DC analysis procedure. I think we don't need to emphasize the concept of the DC circuit anymore because we have been quite familiar with it. So with a DC supply and get rid of all of the AC's inputs and the capacitors, we will be able to find a DC circuit in where we obviously open the capacitor and then short the input AC voltage source and open the AC current source, if any. Okay. And then we are going to find the voltage and current. In MOSFET, this section, what we want. We want to find VGS, want to find VDS, and ID, remember? However, in the Bjt here, what we want is VCE and IC. VC and IC. So obviously, we are short of one node, right? In MOSFET VGS, now we should kind of looking for VBE, right? Correspondingly. We don't need to find it because of this. Now look at this equation. What do you find? For a fixed material, the VB is a constant value, will be given. Remember in the lab today, for a silicon material, VBE equals to 0.7. For germanium, what's the VBE value? Anyone still remember? Today's lab.
Was it 0.3?
Good, very good. Anyways, it's lower. It's lower. Okay? It's different material. You fix the material, then VB is fixed. Of course, it might be VEB, depending on NPN or PNP, right? It's nice. And this part is becoming easier. However, the bad news is what? IB is not zero. IB is not zero. Okay. In MOSFET, IG is zero, right? Not ID. IG is zero. In Bjt, IB is not. Okay, that's the downside, right? It's always, this is the upside, the voltage. The downside is the current, right? IB is not zero. But we have two current gain equations here. Never forget to use. Just like what? Just like the saturation current equation back in the MOSFET, right? There's something fixed there. You just copy and paste. Right? Never forget to use it. Okay? Besides, what you can do? It's quite similar to the MOSFET again. You're gonna very likely need the voltage at the base, not the gate this time. However, how to find the voltage at the base? You need to be careful. You are not allowed to use the voltage divider anymore. Instead, you need to use the KCL. KCL, of course, works fine for MOSFET too. However, voltage divider was easier, right? But now voltage divider cannot be used. Instead, you have to use the KCL. Find VB. And after finding VB, you are going to the VBE loop KVL, so just like a VGS KVL in the MOSFET. And then you also need a top to bottom KVL to containing the VCE. And you have the feeling or the sense that it's quite close to MOSFET. Do you have that kind of feeling and sense so far? No? Or yes? Anyone?
Sorry, what was the question?
No, my question is, do you have the sense or feeling like everything so far is pretty close to what we learned from MOSFET?
Oh yeah, yep. Sorry.
Analysis, yep. The analysis, the pattern, the procedure, the idea. You see here, we're not looking for VG, now we're looking for VB. We're not looking for VGS loop KVL, we're looking for VBE loop KVL. And we also need the top to bottom KVL. You see? Same arsenal, basically. And also the third step is don't forget to check the what? Check this time is not checking the saturation. You're checking what the active, right? A different name, remember? And this checking is easier. This checking is easier too. That checking is easier too. VVC. Now you're comparing the VCE with the VCE saturation. And the VCE saturation voltage, it's very, very easy. It's a constant will be given or assumed to be 0.2 volts. Okay. So it's not like the MOSFET. Okay. The saturation voltage is it need to be calculated. No, VCE saturation voltage is given here. Very easy. So if everything makes sense, then we can move on directly to the example. I think it's really fairly easy here. How about I give you guys 5 minutes to do this yourself? How to see how far you can reach, and then I will present the solution and explain. All right, 5 minutes. Start. And beta is given. Right, this is the current gate, remember? BB is given as 0.7. And find IC and VCE. Is the formula needed? We have two formula. Do we need them? All right, then if not needed, just carry on. See, what can you have? All right, we are seeing some of you got some results. To be very honest, I can't remember what is the result. Let's see, step by step. Okay, so I'm showing the equation one by one. Okay, these are the three equations that we're going to use. First equation is what? First equation is so-called VBE loop KVL. VBE loop is down here, right? VBE loop is down here. From this 4 volts all the way down to the ground, going through RB voltage, going through VBE, right? So total 4 minus 0 equals to IB times RB plus the VBE value, which is 0.7. This is the first equation, VBE loop KVL. Because the VB is given. We are not using the so-called KCL to find VB. No, we don't need. It's already given. Second equation is the current gain, right? IC over IB equals to the beta 200. Okay, this is the second equation. Third equation is what? From top to bottom KVL, right? Top 10 to bottom 0 equals to summation of RC voltage plus VC, right? So RC voltage is 2K times IC. So from here, what we are seeing, IB, IC, and VCE, 3 equations and 3 unknowns, right? So first of all, any questions regarding these equations? Nothing beyond the previous page, the procedure provided arsenal, right? Nothing beyond that. Any questions here? All right, if these are clear, then just the algebra. IC turned out to be 3 milliampere, and VCE is equals to 4 volts. Right. So here we go. Of course, don't forget the very last step is checking. And as I said, VCE saturation voltage is a very small voltage. We can feel free to assume to be 0.2. 0.2 volt. So VC is obviously 4 is way bigger than 0.2, so it is active. Done. Any questions? All right, if no questions, let's do one more actually. Well, seems too easy. Where's the catch? Well, of course, in the next exam, you're gonna have a lot of catches. I'm kidding. I mean, example 1, what do you expect, right? We can't have the difficult level reach the ceiling from the beginning. Otherwise, students are scared away, right? Anyways, example 2, go ahead. Daniel, what was it?
Can we always assume that VCE sat is 0.2 volts?
Yes.
Okay. Thank you.
Except otherwise being told.
Okay.
All right, go ahead. Example 2. This time, give you 3 or 4 minutes. Any results from anyone? All right, let's see together. Okay, I don't know if Kevin's result is right, but let's see. So here are the equations, 3 equations, pretty much following the same idea we have done in example 1. So this time is looking for VEB loop KVR. VEB loop is where? Is up here, not down here anymore. It's up here, right? Up here, then how to write this KVL? Past KVL. Beginning point voltage potential 5 minus the ending point voltage potential 1.5. The difference between these two equals to VEB plus the voltage across RB, which is equal to IB times RB. Okay, this is how we come up with the first equation. Second equation is IC over IB equals to the beta. Third equation is top to bottom. 5 minus 0 equals to the VEC plus voltage across RC. Okay. Any questions regarding the equation? And if these are fine, then we go ahead. The resulted IC is 0.5 milliampere. VEC is 2.5 volts. Right? Okay, good. That's fine. And then what we need to do is once again check and done. Right. But to be very honest, it's not very easy to become saturation in Bdt. Not as easy as the MOSFET to non-saturation. Okay. All right, any questions? Yeah, seems pretty straightforward so far. All right, thank you for attending today's lecture, and talk to you guys next week. Thank you. Bye-bye now.